So today we are going to study important reactions of haloalkane and haloarene. First reaction that we will study today is Groove's process. Now this Groove's process is actually a very important process for converting alcohols into haloalkane. Second, we will study Finkelstein reaction. Important reaction in which the product that we get, they are iodoalkanes, iodo derivatives of alkanes. Third reaction is Swartz reaction, a reaction which help us to convert normal chloro and bromoalkane into fluoro derivatives. That means fluoroalkanes. Next, we will study Friedel Crafts reaction. There are two reactions in this category of Friedel Crafts. First reaction, Friedel Crafts alkylation. Second reaction, Friedel Crafts acylation. Then we will study Wurtz reaction, Fittig reaction, and Wurtz Fittig reaction. All these reactions are important reactions of this chapter, haloalkane and haloarene of grade 12th. So let's start with the first reaction, which is our Groove's process. So what is this Groove's process? What this Groove's process is for? So Groove process, it helps to convert alcohols to haloalkanes. Our goal is to convert alcohol to corresponding haloalkane. Now to conduct this reaction, we react alcohols, that means ROH, where R stands for alkyl chain. That means this R, it can be bond CH3, it can be bond C2H5, etc. This R is actually your alkyl chain. Now this alcohol, we have to react this alcohol with HCl, or we can say HX, hydrohalite. Okay? Where this HX can be HCl, it can be HBr, it can be HI. So for this example, I'm just taking this HCl. Okay? Now, when we react it in the presence of anhydrous ZnCl2, zinc chloride, and the product that we get is this hydrogen. It combines with this OH hydroxyl group to give us H2O or HOH, and this R, it takes this Cl. So we get RCl. That means our alcohol is getting converted into what? It is getting converted into corresponding haloalkane. So this is what we call Groove's process, and this Groove's process is actually a very important process. Now, what more you need to know about this Groove's process? Let's discuss about that. Starting with important reagent, which is called Lucas reagent. What is this Lucas reagent, and what is the formula of this Lucas reagent? This is very important question. So this anhydrous ZnCl2, anhydrous zinc chloride, along with HCl, this is what we call as Lucas reagent. And this Lucas reagent is required to convert alcohol into corresponding haloalkane. But there is something additional to the use of this Lucas reagent, because it is chemistry. Chemistry has a lot of exceptions. Chemistry has a lot of concept within concepts. So now let's start. First, suppose that we have a primary alcohol. We have primary, that means a 1 degree alcohol. What is this 1 degree alcohol? 1 degree alcohol means alcohol in which our functional group, which is OH, hydroxyl group, it is attached to a carbon atom. It is attached to a carbon atom which is directly connected with only one carbon atom. So these kind of alcohols are called primary alcohols. Now I am reacting this primary alcohol with HCl. This HCl is in aqueous state. Now I will take anhydrous zinc chloride ZnCl2 as a catalyst, and what product will I get? This OH will get replaced by Cl. So that is going to be my product. This is CH3, this is CH2, this is CH2, and here we have our Cl. This OH got replaced by Cl. And as a byproduct, we have H2. Now, because we are using primary alcohol in this, so to convert primary alcohol into corresponding haloalkane, we also require to heat. We also require to provide heat. Without heat, this reaction will not take place with primary alcohols. So, for converting primary alcohols into corresponding primary haloalkane, these are also 1 degree haloalkane. So, when we are doing this conversion, we require to provide heat to the system. Without heat, this reaction, Groves process, will not take place with 1 degree alcohol. Now, if we have 2 degree alcohol, if we have secondary alcohol, so in case of secondary alcohol, we again will take one alcohol. This is CH3, CH, CH3 and OH group is placed at the middle, and here you can see the carbon to which this OH group is associated, this carbon is directly connected with 2 other carbon atoms. That is why this is secondary alcohol or 2 degree alcohol. Okay, this is 2 degree alcohol. Now I will react this 2 degree alcohol with aqueous solution of HCl, and again in the presence of anhydrous ZnCl2. But the catch is that in this case I don't require heat. This reaction will occur at room temperature. It will occur at room temperature, although the reaction will take 15 to 20 minutes. It is not going to be a rapid reaction. This reaction will take 15 to 20 minutes, but it will occur at room temperature without supplying any heat. Now what is the product? In this case, I'm going to get secondary haloalkane. That means this OH will get replaced with Cl of HCl. As byproduct, I will get H2O. And here what I'm getting is 2 degree haloalkane. This is our 2 degree haloalkane. So remember this, sorry, when we are converting 1 degree or primary alcohol into corresponding primary haloalkane, we require anhydrous ZnCl2 along with heat. यहाँ पर heat required है. When we are converting secondary 2 degree alcohol into corresponding 2 degree haloalkane, heat is not required. This reaction will occur at room temperature, although this reaction will not be a fast reaction. It will take 15 to 20 minutes. Now, if suppose I have 3 degree 3 degree alcohol, I have 3 degree alcohol, that means tertiary alcohol. Okay, 3 degree alcohol or tertiary alcohol is what I have. I'm giving you the example. This is CH3 group, this is CH3 group, this is CH3 group, and here we have OH. Tertiary butyl alcohol is what we call this compound. So this is 3 degree alcohol. Now to this 3 degree alcohol, I am adding HCl. And again, HCl is in aqueous state. Here, in the case of 3 degree alcohol, we don't require ZnCl2 as catalyst. Okay, we don't have to supply any heat. We don't have to supply or provide any catalyst. This reaction will occur without catalyst and without heat. Okay, and what are the products that I will get? This OH will again get replaced by Cl, and I will get H2O as byproduct. Okay, so whenever we are trying to convert 3 degree alcohol into corresponding 3 degree, that means tertiary haloalkane, I don't need any catalyst. In fact, this reaction will occur fast. This is going to be a fast or a rapid reaction. It will not take time to occur. Okay, so this is all about Groves process, which is first important reaction of haloalkane and haloarene. Okay, so please copy the board. I'm giving you some time to take the screenshots. This is with primary, this is with secondary, and this is with tertiary. Now moving to the next reaction, which is Finkelstein reaction. Now, if we want chloro derivatives of haloalkane, that means RCl. If we want bromo derivatives, that means RBr. They are easy to obtain. They are very easy to obtain. There are different methods by which we can obtain chloro and bromo derivatives of haloalkane. But to obtain iodo derivatives and to obtain fluoro derivatives, we need specialized reaction. Finkelstein reaction is one such reaction in which we convert chloro or bromo haloalkane into corresponding iodoalkanes. So in this case, this is a very simple reaction. I have CH3Cl. This is basically what? This is basically RCl. The CH3Cl, that means methyl chloride, can also be written as RCl. This is going to react with NaI, sodium iodide. Okay, this is going to react with sodium iodide. Now, this reaction will take place in the presence of acetone. Okay, it will take place in the presence of acetone. I'm drawing the structure of acetone. This is CH3. This is C double bond O, CH3. Carbonyl carbon with CH3 group on both the sides. So what I will get, this I will actually replace Cl and this Cl will replace I. So I will get CH3I, that means iodomethane. Along with this, I will get NaCl as byproduct. Here I can write it as Ri plus NaCl. So this reaction, Finkelstein reaction, is a reaction in which chloro or bromo derivatives of haloalkane, okay, these are chloro or can be bromo derivatives of haloalkane, and we convert them into iodo derivatives of haloalkane. And this is all about Finkelstein reaction. It is a very simple reaction. Now moving to the next one, next important reaction, that is Swartz reaction. Now Swartz reaction is a reaction in which we convert chloro derivatives and bromo derivatives into corresponding fluoro derivatives. Okay, into corresponding fluoro, R bond F, fluoro derivatives. Okay, this is what we call Swartz reaction. So let's see how Swartz reaction take place. First, I'm giving a very simple reaction. I have RCl. This RCl is reacting with AgF, silver fluoride. Okay, and it is giving RF plus Ag. The Cl comes here, AgCl. So this is the conversion of chloro derivative into fluoro derivative by reaction with AgF, silver fluoride. In place of AgF, this reaction can also occur in the presence of SbF3, antimony trifluoride. This reaction can also occur in the presence of Hg2F2. And all these reagents, they help us to convert chloro or bromo derivatives into corresponding fluoro derivatives. Now there is one important reaction which is associated, and it is sometimes asked in the fill in the blanks, or the left part is given and the right part is asked. That means reactants are given and in the question products are asked. So let's see those examples. First I have CCl4, carbon tetrachloride. Now this carbon tetrachloride CCl4 is reacting with SbF3. This is antimony trifluoride, which is our reagent. Now what we will get is CCl2F2. I'm drawing the structure. This is carbon at the center. On two valencies we have chlorine. On other two valencies we have fluorine. This is basically a chlorofluorocarbon, CFC. Okay, ferron 12 is the name. So this is actually a CFC. So we get CCl2F2 along with SbCl3. Now if you will balance this reaction, I'm not wasting time in balancing the reaction, you will get the overall reaction that looks like this. 3 molecules of CCl4 reacting with 2 molecules of SbF3 to give us 3 molecules of CCl2F2 and 2 molecules of SbCl3. This is how the balanced reaction looks like. So this is basically the conversion of carbon tetrachloride by the reaction with this antimony trichloride into CFC, chlorofluorocarbon, specifically into ferron 12. Okay. Another important reaction which is associated with this Swartz is this one. This is a benzene ring. This is benzylic carbon that has 2 hydrogen atoms. Sorry, that has 3 chlorine atoms associated. This is Cl, this is Cl, this is Cl. Okay, so this is what? This is trichloro benzophenide. Okay, trichlorobenzophenide. Okay, now we can also call it trichloromethylbenzene. I'm also adding one more name. This is also trichloromethylbenzene. Okay, now this is reacting with SbF2. This is SbF3. This is reacting with SbF3. Or it can also react with HF here. The product that we will get is something that will look like this. This C. Now each of the chlorine is replaced by fluorine. This is what? This is trifluorobenzophenide. Or it can also be written as trifluoromethylbenzene. So these two reactions are important reactions which are associated with Swartz. First is the conversion of trichloromethylbenzene by the reaction with SbF3 into trifluoromethylbenzene, and another one is the reaction of carbon tetrachloride with SbF3 to give chlorofluorocarbon. Okay, and this is what Swartz reaction is. Please take the screenshot. Swartz reaction, conversion of chloro or bromo derivatives into into fluoro derivatives. Now next is Friedel Crafts reaction. So in Friedel Crafts reaction we have two different reactions. Reaction number one is Friedel Crafts alkylation. Reaction number one is Friedel Crafts alkylation. So what is this Friedel Crafts alkylation? First of all, in case of Friedel Crafts alkylation, we have alkyl halide which is reacting with chlorobenzene or with toluene also. So I'm showing both the reaction. This is our chlorobenzene. This is CHLORO benzene. Now chlorobenzene is reacting with CH3Cl. That means chloromethane or methyl chloride. Let me write the IPAC name, which is chloromethane. So it is reacting with chloromethane, and you can see that whenever we have a aromatic ring or whenever we have carbon-carbon double bond, to that carbon-carbon double bond nucleophile will never attack, because nucleophiles are negative in nature. Nucleophiles are negative in nature. Now these nucleophiles, these are actually repelled by the pi bond which is present in a double bond. Suppose we have carbon-carbon single bond, we know that this bond is going to be sigma bond. If we have carbon-carbon double bond, one bond is going to be sigma formed by head-on overlap, another bond is going to be pi bond. And because pi bond is there and pi electron cloud exists, so nucleophiles are always repelled. That means in this case, this Cl cannot get attached to this benzene ring. CH3 has to attach. Okay, so the CH3Cl, it will break into CH3 positive carbocation and Cl negative, and this Cl negative will not attach to this benzene ring. This CH3 will actually attach. Okay, so this reaction is taking place in the presence of anhydrous AlCl3, aluminium chloride, and what is the product that we are getting here? The product that we are getting is this one. This is our benzene ring. This is chlorine which was already attached, and we have CH3 here. And the second product that we can have is like this. This is our benzene ring. This is Cl attached, and this is CH3 group attached. Okay, what is the difference? Here the CH3 group is introduced in the ortho position, adjacent to the first functional group. Here the CH3 is introduced in the para position, opposite to the existing functional group. And as a byproduct, we will get HCl. Why? Because from this carbon-carbon double bond, one H will get released, and when this H will get released, it will leave a carb anion, a negative charged carbon here, to which this positively charged CH3 will attack. Okay, so this product, which is called, I'm giving the names here. This first product is orthochlorotoluene, because this chain CH3 attached to this whole benzene ring is called toluene. So this is orthochlorotoluene, and this is parachlorotoluene. Parachlorotoluene. In this case, this parachlorotoluene is going to be our major product, and this orthochlorotoluene is going to be our minor product. NaCl is the byproduct. So this is the Friedel Crafts alkylation when it is taking place with chlorobenzene. Now, if the same reaction is taking place with methyl benzene or toluene, then what will happen? So this is what we call toluene. This is toluene, CH3 attached to benzene ring. Now on this toluene, again this CH3Cl, methyl chloride or chloromethane, is attacking. Again, the reaction will take place in the presence of anhydrous AlCl3, and the products that we are going to get are two different products. First and the second one. This CH3 was already here. This CH3 was already here. Now in the first case, जैसे कि previous case में भी हुआ था, in this first case we will see that CH3 group is attached here. In this case, CH3 group is attached here. So when two CH3 groups are attached to a benzene ring, that compound is called xylene. So we will call it orthoxylene. This is called orthoxylene, while this will be called paraxylene. Okay, and what is the byproduct that we will get? This Cl will get associated to the H which is released, so the byproduct is going to be HCl. Okay, so here we are getting Friedel Crafts alkylation, which is giving orthoxylene and paraxylene. So this is very important. Now next reaction is Friedel Crafts acylation. It is Friedel Crafts acylation. Now in case of Friedel Crafts acylation, we have acyl halide which is going to react. So this is chlorobenzene again. It can be bromobenzene also. So we have chlorobenzene this chlorobenzene is reacting with acyl halide. That means we have CH3 associated with carbonyl group. On other side we have Cl. This is acyl halide, or because I have associated this chlorine here, so I can call it acyl chloride. This is acyl chloride. Okay, so this is our acyl chloride. So reaction is between chlorobenzene and acyl chloride, and in this case also this bond, this CCl bond will break. This C will become positively charged cation, or specifically saying carbocation, and this whole group CH3 double bond O will get attached here. Okay, so first case that we have is, this is our benzene ring. To this benzene ring This Cl was already attached. Again, this is our benzene ring. To this benzene ring, this Cl was already attached. Now here, this group C double bond O CH3 is getting associated at ortho position, and in this case, this C double bond O CH3 is getting associated at para position. Along with this, we will get HCl released. We will get HCl released. Now, in this whole case, this chlorobenzene is converted into what? This is converted into orthochloro acetophenol. Aceto because CH3 is here, phenyl ring because this benzene ring is here, and one because this is actually a keto. We have carbonyl group on one side, we have R, on another side we have AR, that means aromatic ring. While this is going to be parachloro acetophenol. So this is conversion of chlorobenzene into orthochloroacetophenol and parachloroacetophenol. Now, last two reactions, which are also very important reactions. First, I will give you time to just note these reactions down. So this is Friedel Crafts alkylation. First example with chlorobenzene. Second example with toluene. Then we have acylation, where chlorobenzene is reacting with acyl halide, specifically acyl chloride, to give us orthochloroacetophenol and parachloroacetophenol. Now moving on to, I have already covered this, so I'm just skipping the board. Moving on to the Wurtz reaction. Now there are three reactions. First is Wurtz reaction, second is Fittig reaction, and then there is Wurtz Fittig reaction. Now in Wurtz reaction, we have haloalkane. We have haloalkane, and these haloalkanes, they give us alkanes. Okay, so this is conversion of haloalkanes into corresponding alkanes. So I'm taking one example. I have CH3Cl, methyl chloride, and how many molecules of methyl chloride I have? I have 2 molecules of methyl chloride. Now these are reacting with 2 atoms of sodium in the presence of dry ether. Whenever we use sodium, we require dry environment, because sodium, it will easily catch fire if it comes in the contact with moisture. So we have methyl chloride, 2 molecules reacting with sodium to give us CH3 bond CH3 plus 2NaCl. That means each of the chlorine groups, each of the chlorine atoms, not groups, each of the chlorine atom is taken by sodium, and this CH3 will form bond with this CH3 to give us ethane. This is ethane. So this reaction, Wurtz reaction, is conversion of haloalkane into corresponding alkane. Okay. Now moving to the Fittig reaction. Now what is Fittig reaction? In this we have aromatic halides. Okay, that means haloarenes, and these haloarenes are converting into corresponding arenes or diarenes. Okay, we get corresponding arenes or specifically diarenes. So this conversion is called Fittig reaction. So I'm taking one example. We have chlorobenzene. This is chlorobenzene, and we have one more molecule of this chlorobenzene. Same chlorobenzene, we have 2 molecules. Let me just make this ring in a better way. So we have 2 molecules of chlorobenzene. Now we again are going to react this with 2 atoms of sodium, and this reaction will take in the presence of dry ether, because whenever we are reacting with sodium we require dry conditions. And what will happen is these 2 benzene rings they will join together to form dibenzene. Remember this, that these benzene ring will form dibenzene, and in case of dibenzene there is a bond, there is a join between two benzene ring. Okay, so it is going to form dibenzene along with 2NaCl as byproduct. So this is called Fittig reaction. Now when we combine these two reactions, we get Wurtz Fittig reaction. In Wurtz Fittig reaction, we have C2H5Cl. That means ethyl chloride. Ethyl chloride. Now this ethyl chloride is reacting with C6H5Cl or a benzene ring with Cl, chlorobenzene. This is CHLORO benzene. And the whole system is reacting with two atoms of sodium in the presence of dry ether. Now see what will happen. This Cl and this Cl and this Cl, they will go to form 2NaCl. And this part, C2H5, and this part, which is our phenyl ring, this will actually form this benzene ring, and we have C2H5 attached here. So this is our major product, ethyl benzene. This is our major product. Okay, this is our major product. So this is called Wurtz Fittig reaction. In Wurtz Fittig reaction, haloalkane and haloarene react with sodium atom in the presence of dry ether to give corresponding product, along with the release of this 2NaCl as byproduct, or 2NaBr if I'm taking bromobenzene there. So this is Wurtz Fittig reaction. So you may take the screenshot. This is your Fittig reaction, and this one is your Wurtz reaction. So Wurtz reaction, haloalkane into alkane. Fittig reaction, you have haloarene into corresponding diarene or arene. Then you have Wurtz Fittig, haloalkane, haloarene, dry ether, sodium metal, and you get corresponding products. So these were all important reactions of this chapter called haloalkane and haloarene. In this video, we have covered Groves process, we have covered Finkelstein reaction, we have covered Swartz reaction, we have covered Friedel Crafts reactions, and we have covered Wurtz Fittig reaction. Thank you.